I'm going to look at a further statistics question from a paper from 2024. Today I'm going to look at question 4, which talks about the probability of rolling a dice. So let's look at this question together. Every morning, Jithaka repeatedly rolls a fair 6-sided die until he rolls a 3 and then he stops. So very quickly, we're able to identify that this is a geometric distribution because we are repeating the number of attempts until we succeed. So let's see what the parameters are for this distribution. Rolling a dice, fair 6-sided dice, means that the P, probability of success, is 1/6. So we can immediately answer some of the questions. I'm going to highlight the relevant information given in the question. Fair 6-sided die until he rolls a 3. Okay, so part A asks for the distribution. So as I said, is a geometric distribution with P equals 1/6 because it's a fair 6-sided die. Because X is given as the number of times he needs to roll to get to a 3. So X is geometrically distributed with parameter 1/6. So that's part A. Part B, working out the probability of X less than or equal to 3. Now, there are two ways to do this. The slightly long-winded way, as you might know, is P of X equals 1, P of X equals 2, plus P of X equals 3. So we can work that out because we know that for X equals 1, simply that's just one success, so that's 1/6. P of X equals 2, so that means failure, 5/6, and then a success, so that's 1/6. P of X equals 3, that's 2 failures and 1 success, so on and so on. And therefore, we will get 91/216 by working out these fractions. A slightly simpler way of doing that, part B, we can simply say probability of X less than or equal to 3 is simply 1 minus the probability of X greater than 3. Now, the probability of X greater than 3 means that for the first 3 dice rolls, we're not going to see a 3. So basically, we get failures for 3 times, which is 5/6 for 3 times, and that's an easier way to get to 91/216. So that's part B done. Looking at part C. After 64 mornings, Jithaka will calculate the mean number of times he rolled the die. Estimate the probability that the mean number of rolls is between 5.6 and 7.2. So this is asking us to look at the mean number of rolls. So effectively, we need to use central limit theorem because we want to look at the mean number of rolls denoted by X bar. So let's call that X bar, mean number of rolls. First of all, to deploy central limit theorem, we want to work out expected value of X. Expected value of X in central limit theorem is simply the mean of your underlying distribution. So we know that mean of underlying distribution E of X is 1/P. That's a property of a geometric distribution, or you can actually get this formula from your formula book. P equals 1/6, so that's 1/1/6 equals 6. The variance of X is, again, given by the formula in your formula book, 1 minus P over P squared, which is 1 minus 1/6 over 1/6 squared. Working that out, we get 30. So that is our sigma, that is our mu. Central theorem says X bar, so the distribution of the sample mean, is broadly normally distributed with population mean and sigma squared over n. Here in the question, we've been given that n equals 64. Let me put it in green there, n equals 64. So in other words, we know that X bar is approximately normally distributed with mean of 6 and a variance of 30/64. So this is key for us to work out the probability required from the question. So try to answer the question What's the probability that the mean number of rolls is between 5.6 and 7.2? And we can express this like that. 7.2. So plugging this into our calculator with normal distribution with mean of 6, variance of 30 over 64, the required probability, we get 0.6806. So it's broadly 0.681. So that's our answer to part C. Let's give us a little bit more space and look at part D of our question. Nero wants to check Jitharka's die to decide whether or not the probability of rolling a 3 with his die is less than 1 over 6. Nero rolls the die repeatedly until she rolls a 3. He obtains x equals 16. So part D there. Part D is asking us, by carrying out a suitable test, determine what Nero's conclusion should be. To state your hypotheses clearly and use a 5% level of significance. We need to write down our null hypothesis and our alternative hypothesis. From what we saw earlier, we assume that x follows a geometric distribution with probability of success p. Here, our null hypothesis is that p equals 1 over 6, because this is what we're trying to establish. The alternative hypothesis, let's take a look. It's going to be either p less than 1 over 6, p doesn't equal 1 over 6, or p greater than 1 over 6. So let's take a look at the question. It says, Nero wants to check whether or not probability of rolling dice is less than 1 over 6. So that is our alternative hypothesis, less than 1 over 6. What if I need to roll the dice 16 times in order to get a 3? So what's the probability that I need to roll 16 or more times? If this probability is less than 5%, then there is enough evidence to reject H0. So let's work out under H0 what this probability is. Under H0, this probability equals P of x greater than 15. That means that I need 15 times of failures, which equals 5 over 6 to the power of 15, which equals, let's give us more space, which equals 0.0649. And this is greater than 5%. Therefore, there's not enough evidence to reject H0, which means that there is not enough evidence to reject the assumption that the dice is a fair dice.